Entropy is one of the most common challenging topics in physics and thermodynamics. In this video, we will break down entropy into simpler terms and clarify some common misconceptions to make it easier to understand. Entropy is a scientific concept commonly associated with disorder, randomness, or uncertainty in a system. In simple terms, the greater the randomness or disorder in a material, the higher the entropy. However, it's important to note that disorder here refers to the number of possible configurations that molecules in a system can adopt. It does not necessarily mean visual chaos. For example, consider ice and liquid water. In its solid state, ice has molecules arranged in a structure lattice-like configuration due to strong hydrogen bonds. The fixed arrangement limits the number of possible molecules configurations, resulting in low entropy. On the other hand, liquid water lacks this rigid structure. The molecules move freely and can adopt many more configurations. This increased molecule motion leads to higher entropy. Thermodynamic tables often list entropy values for various materials under different conditions such as state, temperature, and pressure, which can help quantify these differences. Entropy is often introduced in the context of the Second Law of Thermodynamics, which states that in any spontaneous process, the total entropy of an isolated system will either increase or remain constant. It never decreases. But what does this mean? Let's revisit our ice and water example. Imagine an isolated system consisting of a cup of water with ice in it. Initially, let's say the system has an entropy of S1. Over time, we know that heat naturally flows from warmer water to the colder ice, causing the ice to melt. When the ice melts, its rigid molecule structure breaks apart, allowing the molecules to move more freely. This leads to a significant increase in entropy. While the liquid water loses some entropy as it cools, the decrease is much smaller than the entropy gained by the melting ice. As a result, the total entropy of the system increases to S2, consistent with the second law of thermodynamics. It's important to note that the second law applies to the total entropy of the entire system, not individual components. This can lead to a common misconception. People often think that the second law means entropy cannot decrease anywhere. However, entropy in one part of the system can decrease as long as the overall entropy increases or remains constant. In our ice-water system, the system starts out of equilibrium, with the heat flowing from the liquid water to the ice. Once all the ice melts, the system reaches equilibrium. But equilibrium doesn't mean that the system becomes more orderly. In fact, it corresponds to a state of maximum entropy. At equilibrium, the molecules in the system have the highest number of possible configurations, with energy and molecular arrangement distributed as randomly and evenly as possible. Thus, an equilibrium system often has the maximum possible entropy. In thermodynamics, we are typically more interested in the change of entropy. The change of entropy for a process can be given by the following equation. Here, Q is the heat transfer during the process, and T is the absolute temperature at which the process occurs. For processes involving large reservoirs, we often assume the temperature remains constant. When the temperature varies, an average temperature can be used as an approximation. For example, suppose 3000 joules of heat is transferred from a hot reservoir at 400 degrees Kelvin to a cold reservoir at 250 degrees Kelvin. The change in entropy can be calculated as follows. The second law has many important applications in thermodynamics. For instance, it's crucial in understanding heat engine efficiency. A heat engine converts heat energy into work by absorbing heat from a hot reservoir, performing work, and expelling some heat to a colder reservoir. The energy balance can then be expressed as follows. To maximize work output, we aim to minimize the expelled heat. However, setting Q2 to 0 would violate the second law of thermodynamics because it results in a negative change in entropy. The maximum value of Q2 occurs when the change of entropy equals 0. Using this condition, we can derive the maximum efficiency formula. This equation tells us the fraction of heat that can be converted into work, with the rest being lost into the colder reservoir. The closer the temperature of the cold reservoir to absolute zero, the more efficient the heat engine can become. But no engine can achieve perfect efficiency due to the second law. By understanding entropy and its role in thermodynamics, we gain a deeper appreciation of energy transformation and limitation imposed by the nature. Whether it's calculating changes in entropy or optimizing engine efficiency, entropy is an essential concept that governs the behavior of systems around us. I hope that this video made the concept of entropy and its applications more clear. Thanks for watching.